introduce the speaker.
I'm very happy to introduce the next speaker. Saneet M. So from Vikram Varabai Space Center, VSSC, Thiruvananthapuram. So Sir did his chemical degree. He joined VSSC Thiruvananthapuram in 1997. Then he is working on the development of electronic energy systems for spacecraft applications. And his scientific and technical contributions are in the area of designing, development, and realization of hydrogen cells, lithium-ion cells, hydrogen fuel cells for space missions in ISRO. He is currently the Group Director of Energy System Groups in VSSC at Thiruvananthapuram. Sir has published several international journals and reputed journals, and then published 2 patents and also written 2 books. He has given several talks in medias and especially in All India Radio. So with this introduction, I thank.
Yes.
I welcome the speaker.
Hello, am I audible? Fine. Thank you very much. I'm not familiar with this kind of a mic because we don't generally speak in classrooms. And at the outset, thank you very much for inviting me for this program. And this is my second presence in SSC. I had the opportunity to give a talk in Tirur conference, I think some 12 years back or so. But the interesting point is the subject I talk, at least some part of it remains the same. So that is the scale in which the scientific or technological aspects take time to get into the real use. In fact, that is the emphasis of my presentation. You may find that there are certain discoveries and inventions take decades and centuries for it to really come to the real fruition. So let me get along, and of course this is going to be a totally different subject compared to what we listened. You are talking about electrons and nanomaterials, but this is not about any specific material. It is going to be totally different and over billions of years kind of time domain. So we talk about the existential crisis these days. So as we know, supposed to move. This one, right? This one. Humans, in fact, life was probably originated some 4 billion years ago, and humans, we are talking about big things, but we have a few millions of years of experience on this planet, and in that, Homo sapiens, we all belong to modern humans. We have just 2 lakhs. So we are the youngest species in this earth. But we made phenomenal progress. That's what I just want to cover in the first slide. We'll just rush through that. So, yeah. So we, from starting to make tools 35 lakhs years ago, having controlled fire 14 lakhs years ago, and agriculture 10,000. You plus see the most critical technologies that probably we developed initially. We don't really understand the technological part of it, but these 3 really formed the basis for humans to be what it is today. We are different from other species because of this. And then, of course, the much acclaimed wheel, then all this coming. And then, of course, these in later part of it came some 200 to 20 years back only. Otherwise, all these were 10,000 and lakhs of years back. And by 1920s, we started sending rockets. Of course, they were very small rockets. Even much before that, that part also I'm trying to cover. And finally, after computer, we reached the orbit, the space by 1957. So that was Sputnik 1 by USSR. So that is the time when we consider the space era is born. So, and that is probably, the reason why I'm talking here today. And yes, this was a tiny steel ball that was sent to space by USSR then. The entire world got startled by this because of various possibilities that it might give. Yes, it is giving several opportunities and possibilities. The details are given here. It was capable of sending certain radio signals to all the radios on the air that day. But today's satellites are capable of much, much larger and higher things that we'll see. So this is the relative size you can see. Compared to that, today's satellite might it be just big as this, half of the size of this room probably. So so those was rocket then. So the history and evolution of rocketry, if you see, it started somewhere in 400 BC, which means some 2,500 years ago. Which is the marker here? Pointer? Okay. So these were the initial precursors of the rocket, at least that's what we consider. These were magic, for creating magic, then it was used. The steam was put in the cylinder and heating was given, and the steam will come out, and this non-living object started moving for the first time. So under your control. That was the biggest invention of the time. People were not able to believe, they believed it as a magic, but it was based on a science. And similar thing happened here as well, and these things happened in Alexandria and all these places. And then parallelly, something was in the cooking in China, where people found some dark objects giving some fireworks. If you put in the fire, that was nothing but gunpowder. It later turned out to be, but they were playing with it. And they, one fellow started putting it in a bamboo stick. Then they found it forms a projectile. Then they thought, why not simply leave it like that? They started putting it on arrows. Yes, it became a weapon then. And then, of course, their soldiers of the time used it as a real weapon in wars. It was used against Mongols. Yes, Chinese won, but Mongols learned. And from Mongols, it went into several other parts of the country, and including, and of course, parallelly, one fellow tried to reach the moon. And even at that point of time, you just imagine. So that was the first time it was used as a transportation system. So you just imagine, though he died, so this very fact that he used it for taking him to moon, that was the idea he used for as a vehicle, in fact. So then Tipu Sultan is also considered to have someone used the rocketry at that point of time against British very successfully, but British learned it from them. So this was one problem with the technology when you use it in a weapon. The one who gets defeated learned the technology and use it again. So that's how it spread all over the world. But subsequently, Germans really took it seriously and worked on it, and so that was it was started with Oberth and all. There were a lot of rocket clubs at that point of time. It was some 150 years back or 100 years back. So this was one German, von Braun. He went on to make the V2 rocket, which created havoc in world wars. And then you see, this is a mathematician, Tsiolkovsky. His equations are used for designing rockets even today. The fundamental equations by Tsiolkovsky. I think he was a school teacher. And this is the one man who spearheaded a Russian USSR space program until about 65, until his untimely death. So under his stewardship, USSR achieved all the first. The first satellite to be put into orbit, first human to go to space, Yuri Gagarin, Valentina Tereshkova, the first lady, Leica, the dog, everything first. US was totally defeated on all this, but in 65 mysteriously Korolev died. Their programs started failing, rockets started failing, and then 69, Neil Armstrong was in space. So there are several other stories playing behind it. So when we say space, this is what we mean by it. What you see is the Earth's cross section, and when you cross this 100-kilometer, which is called as Kármán line, you have crossed the atmosphere and reached space. And of course, the air density, etc., varies almost proportionally, and of course the concentration of different gases too. You see the ozone layer that we'll be talking about. So this is coming here somewhere in stratosphere. So for understanding the distance. So subsequently, so many developments in space. I already touched upon a few of them, and we were also, and this was possible due to numerous powerful launch vehicles. Unlike the tiny small rockets which was used by Chinese Tipu Sultan and all, and the V2 rocket itself, this was the real technological marvels, weighing hundreds of tons, 300, 500,000 tons they were weighing as when they were lifting off. So very huge. It will be going to about 15 to 20 story building height, about 4 to 5 meter diameter, and weighing about 500 tons. So these mighty vehicles, several of them, we have by different countries. Their liftoff capabilities are shown here. So in terms of the kgs and tons, you can see you have the Saturn rocket which was used for reaching Neil Armstrong on Aldrin on Moon. It could lift off about 140 tons. That is 140 tons of spacecraft it could carry to low Earth orbit. That's what the capability, and about 50 tons or so to lunar orbit. So then India was not falling behind. Of course, we started late. By the time Russians and Americans were planning to reach on Moon, or they were already on Moon with certain spacecraft, but not with the man, but spacecrafts, we were just starting with a tiny rocket. You can just understand the size of it from here, our initial rocket. This is the classic picture we used to impress upon how we really did it. We were using bullock carts and cycles to carry. So that's how we started. And what you see here is a very well-known person, Dr. APJ Abdul Kalam. And here again, you can see him here with Vikram Sarabhai. This is Madhavan Nair. So we too have multiple rockets today. The smallest one, SLV, made by Dr. APJ Abdul Kalam under his leadership, ASLV, the PSLV, GSLV, and the LVM-3, the three mighty rockets that we use for all our programs these days. The most recent one, what we launched was this, and SSLV. Each of these rockets are having thousands of systems. Different. They have the engine that powers them, or the motors that powers them, onboard electronics, several electronics boards, computers, software running in them. They have batteries, capacitors, propellants. Almost 95% of them are loaded with propellants, different stages, solid, liquid, cryo. It's very, very complex and jam-packed systems. It takes a year or so for fabricating them, and for integrating them takes about a few weeks, and the launch takes 15-20 minutes. And they reach 2,000 kilometers, 3,000 kilometers in just 20 minutes. You can calculate the speed, which of course they start with 0 kilometer per second and reach 7-8 kilometer per second. So what is the kilometer per hour? You can just work out and understand. That is the velocity with which physics students, you must know the orbital velocity. So we reach. So that is what they are capable of. But this much size is really needed for putting 100 kg, 1000 kg, or maybe 5 tons to space. So that is the the challenge. So, and we have several satellites. Only a very few I have brought it here. Some 100 odd satellites we have launched by now. And this is okay. This is not an updated one. A few of them you may be familiar. Of course, Chandrayaan 1 is something the most popular. So yeah, this is somehow you can imagine a satellite would be orbiting with a beautiful Earth on the background, and these objects are put in this such a beautiful scenario, or maybe a hostile scenario in another way. It is to do a purpose, and these are the requirements, and this is for which we are spending and doing all this remote sensing, communication. In fact, every day, daily life, we use them in one way or the other. When you take a mobile, when you look at the weather data, it is coming from a satellite. It is a ATM transaction. It's a satellite is coming. Even now, internet connection these days, it is going to be given by broadband connection is going to be given by satellite. GPS mostly we use on a daily basis. So you can name it. There is no other place. There is no application where probably space application has not come. It had made its mark. So these things probably the details like meteorology, weather forecasting, disaster warning, and so on. Then mapping of different places and its importance, like forestry, whether it is town planning or water resource management, etc., etc. And of course, agriculture. Apart from the understanding vegetation cover, crop inventory, it is also leading to deciding the export policies, export-import policies. You can understand what is the harvest that is coming in, whether that is sufficient to balance the price. If not, whether you have to import, or if it is going to be surplus, whether you have to plan to export. These things were taking its own time, and it was creating havoc in the market maybe a decade back, or even some 20 years back or so. But today it's not the case. You can get early understanding of this, and you can decide. These are things probably we may not understand. And now nowadays there are warning or inputs given to fishermen, especially on the eastern coast, to make them understand where they can locate fish, so that they can direct themselves and they can make their harvest the best. So using satellite. So it has reached that such a lower level of requirements, and this is probably something we can appreciate better. This kind of color-coded images describing various things like solar insolation, precipitation, leaf area cover, ocean color, land temperature, carbon monoxide, and there is carbon dioxide as well, severe carbon dioxide concentration. So these are the few things that probably is going to really help us in future. Well, we have done this. We are doing great. We have reached the pinnacle of or we are continuously growing, which no other species could do on Earth. We are making great, but repeatedly we have to remember that we have just spent about 2 lakhs years compared to all other species which would have stayed here for millions of years. Dinosaurs or whatever small creatures or animals you take, they have been here for millions of years. We are doing all this within a short span of few centuries, all these developments. But somehow this has started creating its impact. These were our stepping stones, and we have really reached big places. In fact, all of these, in fact, except for this, all these have started making their impacts also in a negative way. So I can just list a few of them. The characteristic of human habitation. I mean, humans, we know, Homo sapiens are believed to have been born in Africa, Eastern Africa. In fact, they spread to Europe, spread to eastern side, came to India, Indonesia. They reached Australia. Even when they didn't have a support of animals, or they didn't have a technology. Some 30,000, 40,000 years back, they reached Australia, covering the oceans, maybe through a glacial period. They reached America. By 15 or 20,000 years ago itself, humans reached almost all continents without any technological help. Technology started much later. The characteristic of their, reaching out to all these continents have been destruction of flora and fauna of this. Australia has lost, it was a secluded continent having its own exotic species. Kangaroo is the only one that is remaining today, which you don't find anywhere else. Everything else lost. Either because our own poaching for food, or because the plants or the animals we nurtured, they made them prey, and anyway we lost them. That is species getting extinct, whether it is plant or animal. So that is one aspect. Then changing topography and land use, it is continuously going on even today. Kerala today is substantially different from some 10 years back, which itself was substantially different from 20 years back, and so on. You can understand this area itself, how much change it is going on. So that creates its own so much of havoc. I don't need to explain all this, that's not the subject today. Destruction of biodiversity, partly covering the first one, and pollution. In fact, all these were, to a great extent, they were considered as local problems. And they were locally managed because their impacts were thought to be, local, and so it was sort of left like that until recently. But now we know whatever we do it, even if you scroll reels on mobile phones, you are adding your carbon footprints. You are bringing down the possibility of your survival. So even the smallest thing what you do today, because you are not doing it the way a primitive species was doing it. You use an energy produced separately, and you use that energy, and thereby you are adding to the problems of the planet. So ozone depletion was one classic example, and another one was global. When these two came into the limelight, we understood it is no longer a local problem. Our actions are going to be threat for our existence itself. The first time it was identified in ozone depletion, and I am just touching upon that, how we really addressed it. That is a classic example, how we can act upon it and how we can probably address it and escape if you do it fast. And now the problem what we are dealing really hard is carbon emission and global warming. I'm going to touch upon these two in little detail. Probably, little technological aspects also coming in. These things probably many of you know. Ozone 3, 3 atoms of oxygen, 90% of it is in a stratosphere, and it is somewhere in the range of 15 to 35 kilometer range. It is in the tropics, it is in the 25 to 35, it is in the polar region, it is about 15 to 25 kilometer, it is lower. So, and 10% is in troposphere, and that is deadly for all animals. So increasing ozone in troposphere is deleterious for human. Increase in ozone in stratosphere is, at least maintaining that is relatively required. It's essential. And also there is an oxygen-ozone natural cycle with the play of UV rays. Multiple UV rays play a role, UVA, UVB, UVC. So UVC splits oxygen, and one oxygen atom goes and hit with the oxygen and then makes ozone. And then UVB rays expel an oxygen from there, and that oxygen then either combines with this one or oxygen and makes ozone. So this is a cycle that it is going on. This is a natural cycle. This is how the understanding initially it was developed, But still it was not clearly known how the balancing is happening. You must expect that ozone should be continuously building up, which is not happening. And oxygen is much larger proportion, it is available, 21% is available, but ozone is very small. How is this possible? The very first, the whole thing started in 1930. See, the basic chemical and physical process was found by Sidney Chapman, and then it was found that there are some elements, some species playing a role in balancing them. Apart from UV rays, they are also kind of playing a role. In 1950s, this was known. In 1970, 1970, it was felt that probably that is the first time human intervention came into picture. If you use fertilizers, synthetic fertilizers too much, probably there is a possibility of more NO coming from farms, and that can lead to O3 depletion. And people worked on it in different ways, and they were also trying to link it with the supersonic flights. Probably a misguided understanding was going on. So they were not really looking at the real culprit. Again, it took another 4 or 5 years for the real culprit, the organic halogen compounds, to be the real culprit. That was a startling revelation. And by Professor Frank Sherwood, but they failed to identify the real source. They could understand that this is creating a role, but from where it is coming, they were not able to understand. But this hypothesis by the professor and his research scholar, it was strongly disputed by all the industry majors, because they were making CFCs in huge quantities and making huge profit. They made their life really miserable. These people were not able to do their research in the universities because of the pressure from them. But luck was with them. The work was continuing around the globe. US government was really seized of the matter. US started some work on containing CFCs. They understood it is coming from freezers and all that. And then the real shock came when someone found it is not only depleting, there is a hole itself created in the polar region. But they were not able to understand why it is. And it took British Antarctic Survey scientist Farman and this team to really explain why it is happening, and they could bring out the real reason behind it. And then the world started believing. Even then it was not really accepted, but for that they had to wait till the images from satellite. The interesting thing is satellites were getting this data even some 10 years back itself, but because of the lack of science, they considered it as noise, because it was not possible for ozone to be of such low concentration. It's not really a hole, it is an extremely low concentration of ozone in a very specific area of Earth. When you have such a huge circulation of air going on all around the globe, it is practically, physically, they considered physically it is not possible for a hole or such a low concentration to get formed on any specific place on Earth. This was the theory prevailing at that point of time, and so satellite data was considered as spurious, or they didn't look into it. But when the science came, they rerun the whole thing without the filters, etc. They understood some 1970s on, since 1976, data itself, this depletion was seen. So this is something probably, it is of course needed for the sound science, for even the real data to really fully appreciate and understand. But with this, there was no denial, there was no resistance by anyone. It was great going. A lot of global clamor and treaties and efforts and enforcements and so on. And today we have this is the that famed satellite pictures. You can see when they reran, the concentration is going down. See here itself, it has developed and it is growing, and it has reached this stage. So this is from the US satellite, and I don't know whether this was a video. Yeah, it's playing. You can just have a look at it. Different years, it is showing the concentration. The blue indicates it's very low. It is shown in ozone unit. It is nothing but the ozone molecule required to create 10 micrometer thickness of pure ozone at 0 degree and 1 atmosphere pressure. So it goes below 100 ozone in which is considered as a hole. I mean, it cannot really prevent UV rays. So even today, there is a risk for New Zealand and all to get exposed in September-October period. That's the time where, because of the circulatory systems, there is a pocket getting formed, and the low concentration is occurring in the polar region. It's a kind of chemistry, physics, and dynamics, fluid dynamics, and it's a combined subject. So this is one of the 2024 picture, but the point is that it is continuously, the maximum size each year it can grow, and the concentration that it can, the lowest concentration can reach is coming down year by year. So there is a continual progress. So it is in the right direction, it is going on. So the 2024 latest picture, you can see it is still there, Antarctica, and you can see even South America tip is nearly, very close to that. And these are all the pictures from satellite which could, this is the prediction given by one of the topmost scientists in this. She was working with NASA earlier, and now she is with MIT, one of the vocal persons for this. And this is what is expected, and it is by 2065, considering everything is going as it is today, we expect it will go back to the, normal, pre-1970, 1950. So that is what we are expecting. But 2040 itself, tropic region will reach the normalcy. Polar region will take several more years. But one issue here is that still satellites are able to pick certain hotspots of CFCs. Even with all these embargoes, all these regulations, somebody is still making CFCs. So, but you cannot escape satellites. It is able to find certain hotspots, certain concentration buildup. It is able to see. That is being addressed these days. Next big thing, global warming, I said. This is a tough nut. Again, a timeline for our research interest. We are just putting it here. It has crossed 100. It is crossing 100 years now. This work. This is what I said. The fact that greenhouse effect was first discovered in 1824 by Fourier, and the role played by carbon dioxide and water vapor was understood in a small experiment, laboratory experiment by Tyndall in early 60 itself, 1860. And a lot of additional work happened, and even climate modeling happened by 1930. We call it Milankovitch cycle, which captures the carbon dioxide cycle over glacial period, etc. Now, so it's famous Milankovitch cycle. And in 1957, you see, this idea came. Human beings are carrying out a large-scale geophysical experiment. It's not an intentional experiment, but it turned out to be doing an experiment of such a large magnitude, a very costly one indeed. Today, what we are following is carbon dioxide concentration, and it is called Neeling curve. What you see here is the Neeling curve, and this was developed by a person called Neil. So that's why it is Charles David Neeling. And 74, as I said a little earlier, chlorine's effect was known. Chlorine containing compound is one of the highest warming potential greenhouse gas. So, even before we debated CO2, warming potential of chlorine containing gas was discussed. And by 1990, IPCC report started coming. First report came, and I think fifth or sixth has come recently. So larger global research, one of the biggest research, I think such a magnitude of research is needed to take us out of this issue. Started happening. It is going in a good way. It has brought out so much of science about global warming, and yeah. So and then Kyoto Protocol and so many other regulations coming into picture. This is just to link it with energy use. There is an exponential rise in the last 100 years or so, or 150 years. You see, the reason is attributed to the fossil fuels, and it is exponentially hand in hand. It is going, energy use as well as greenhouse gases. You may see we were around 250, 225, 250 ppm of carbon dioxide in pre-industrial era, even over thousands of years of history. But today we are 425 ppm. So much of a spike in just about 100 years. And it's energy use which is contributing. So this is what, this again is a video. If you can just click that, probably. While it is getting played out, you can just appreciate, the increase in carbon dioxide level. What you show, the curve is each year seasonal cycle. In summer it goes up, and there is a small coming down in winter and all that. So, and you can see in two representations, initially this kind of an increase, and then over the years later, it merges into that. Meanwhile, through Earth observation satellites, how space application is playing a role. Of course, this is data generation and representation, the way we can appreciate energy balance we are able to make, because we get a global picture, ocean health. We are able to precisely, monitor each of the gas emissions. Climate indicators, there are several climate indicators like sea level rise, ice melt, and emission for sources, hotspots we can identify. This is something, and there are spin-off technologies. This is one I would like to, a couple of slides I would like to show on this. For controlling and greenhouse, not only just understanding how it is happening, our technology probably can make some changes as well. So, and of course, it gives us an idea about how it has happened to other planets, so that we can prevent it from happening here. There are histories of Venus, Mars, Titan. Some places it has gone out of hand, go to 464 degree increase, whereas what we need is a balance of about 30 degree from its black body radiation temperature level. It has to have a greenhouse gas delta of about 33 degree for us to be comfortably living here. But you can just look at how it is. Then the last one, whether we can have a colony beyond Earth to escape from all these hurdles. A very fancy idea. If time permits, I can touch upon it. These things, what is greenhouse carbon dioxide emission. There was a balance, but continuous use of fossil fuels, exponential rise in carbon dioxide. There is no coming back. It is not part of the biosphere. It is coming from underneath the crest. So it has led to, this is what really we started understanding. We were not looking at the carbon dioxide. We were suffering from this, and when we look back, and then if this is something simple you can appreciate. See, unknowingly we were going for a cleaner fuel to reduce the emission. We were not planning that, but this is how it was going. You see, this is what we moved over, and now we have reached CNG, and just look at the complex formula of that. And one characteristic thing you can understand is that the complexity of the molecule has come down. That makes the burning more and more efficient, closer to 100%. Second thing is carbon to hydrogen ratio continuously coming down, and also carbon number is coming down. It has reached a single carbon atom here. Of course, what is the next? It is without any carbon. That is simple hydrogen. So we know you can combust hydrogen, you will get only water, no pollutant. And this one, if you use it in an electrochemical system, you get electric power, and it was discovered in 1839. Still, we are just talking about in this kind of presentations. And both these technologies were proven decades back in space technologies. We have been using it for so long, effectively for various missions. You can understand the famed Apollo missions to moon carried fuel cell. It was powered by fuel cell. If without fuel cell, that mission would not have been possible at that point of time. That was in 69, in fact 65 onwards. And it has also powered space shuttles which carried hundreds or 150 space travelers to space and brought so much of science. So that's what very reliable and capable technology, but we are still finding that it is a subject of talk even today. I'm not explaining all this. It's simple. Hydrogen and oxygen, they're not meeting each other. They electrochemically combine, produce, it's an electrochemistry. So one of the highest efficiency you get, 80%, and practically about 60%. But from where hydrogen can come? Hydrogen is clean, but hydrogen is not present in the atmosphere. So from where you can get it? These are the various sources out of which now there is a color coding. Today, gray hydrogen is the one is the maximum what is being produced. About 95% of today's hydrogen production is from steam methane reforming. So even hydrogen is clean, its source is not really clean. So you throw out carbon somewhere. It may not be at the real place where it is used. So that's not the way. The right way is to split water, and that's called green hydrogen, using electric energy, that is solar water splitting, electrolysis. So now the idea has come, if you combine, there is a spurt in the growth of renewable energy. That renewable energy, if you can use for splitting water, then effectively you can produce hydrogen on one hand, and also you can store the renewable energy which is variable in abundance in a practical way. You can transport that energy, you can produce energy somewhere else. So this is a green hydrogen economy. You can use solar panels, wind, etc., use an electrolyzer, use water, produce hydrogen. You can put it into cars, apartments, industry, and grid. So this is called a green hydrogen economy, which is totally greenhouse gas emission free. And not only that, you can produce so many chemicals which are being produced today using like methane and things like that. Hydrogen required for it is coming from methane. So again, you can clean those dirty processes. So ammonia, though it is nitrogen and hydrogen, it is CH3 is split to make ammonia. So today's ammonia is not clean. It has a huge carbon footprint. But if you adopt green hydrogen ammonia making, which is used for all the fertilizers, it comes into several gigatons. So you can clean, and just 2 slides. So now cars, assume it is powered with hydrogen, and they are running on fuel cell with so high efficiency. 90% of the cars worldwide are simply parked. They are not running. Now, if hydrogen is there in abundance through pipelines, if we reach such a stage, then these parked cars, you can switch on the engine and generate electric power. It can be put to the grid. So studies have shown that even a portion of the cars, it has taken place in US, if you use this way, the entire power requirement of US can be met. Just imagine the case for India then. You don't need a thermal power plant. You don't need a hydel power plant. You don't need anything else. So this is like, once computers are sitting on our desk, now all the computers, all the mobiles are all interconnected through internet. So this is something like that, an energy network you can think of. A revolutionary idea. So another one is you can have a fuel cell electrolyzer integrated system sitting on your rooftop. If you use water, some quantity, and use solar panels that deployed on your roof, you can generate hydrogen during daytime, use that for producing electricity during night time. A continuous power, you may have to make up that water occasionally. You don't need to depend on any electricity boards or anybody. So this is another revolutionary. There are so many destructive or disruptive possibilities that could emerge. So now we can become energy producers. Each individuals can produce energy, can sell the energy. So there are so many possibilities coming. So if you do this is the prospects you have. Greenhouse gas emission, it is supposed to go this way. If you use all this, you can bring it down to this, to a kind of a prehistoric scenario. But this is too optimistic. This is not going to be a practical reality. If we are able to contain at least the rising greenhouse gas, probably we'll be through, because we are already touching 1.2 degrees, and we are certain that whatever we do, even if we stop fossil fuels even today, the temperature will continue to rise, because there is a lag in the cause and effect, at least some 10 years or so. Next 10, 20 years, temperature will continue to rise. We can only hope that it will not cross a critical point, because there is a gigantic carbon store sitting beneath the sea in the form of carbonates. If those sleeping giants are waking up, temperature is going, carbon dioxide, carbonates can get splitted because salinity of sea is increasing. If that carbon dioxide is getting into the atmosphere, then it will be a Venus scenario for Earth. So no species would be able to survive. So it is not a time for talking, in fact. So I think I'll stop here. So in case any questions, happy to answer.
Now the session is open for the questions. If any queries are there, sir would love to clear our queries.
Silence, because it is shocking the way things are going.
Yeah.
I think questions will come, but it may take some time.
Yes.
Because I think all of us are in a state of shock. It's very disturbing.
Very much, it is.
Thank you very much for explaining it so beautifully. Really very nice one.
Thank you.
Thank you so much, sir. That was really impactful and sharing us such insights, and it really made us think like on what state we are. That's really true. So thank you so much, sir. As a token of appreciation, we would request our chair and co-chair to present a memento to our esteemed speaker. I request sir and ma'am to do the honor.
Thank you for